Welcome to Data Science 1, Probability, the normal distribution. Things you're going to need to remember: sample space, what a random variable is, a cumulative distribution function, and a probability density function. All right, so we're going to go fishing again. We've been playing with these fish all the way through this video series from the beginning all the way up till now. So I'm going to go fishing, and this is what I might catch. And remember, I'm trying to describe all possible fish. But what could I expect? Well, I could expect that there's a whole lot of fish, and these are on the outside here, that are kind of average-sized fish. They're not big, they're not small. There are some big ones, and there's a few smaller ones. But this is the idea here is when you go fishing or something like that for fish, they're going to have similar weights. Some will be heavier, some will be lighter, but most of them will be in the middle. So we're going to have a few small fish, we'll have a few big fish, but most fish that you're going to get are sort of middle-sized. And that's where this normal distribution idea comes up. It's Gaussian is sort of the other name that goes with it. I will call it the normal distribution, and sometimes I'll call it the Gaussian distribution. Depending on who you're talking to, they'll use the words interchangeably, and you can get really confused if you're not aware that they're the same thing. So here we go. So normal distribution is symmetric. See, its left side looks like the right side if we were to split it down the middle. It's continuous. That's very good for modeling uncertainty with random variables that don't favor large values, so the probability is low out here, and don't favor small values. Probability out here is very low, or the likelihood out here is very low, and the bulk of it being in the center. And this works in lots of cases, and turns out that in some cases the normal distribution will just show up on its own, and we'll see that later. All right, so here's the probability density function for this thing. So it's 1 over the square root of 2 pi sigma squared, e to the negative 1 over 2 sigma squared, x minus mu quantity squared, and x can be any number between negative infinity and infinity. Now, this is the first one we've seen that has the entire real line as its domain. Before, we had to say, well, it would be a positive number because it was a waiting time. Here we have two parameters that control this distribution, mu and sigma, and mu can be any value between negative infinity and infinity, and sigma needs to be positive. And this is often written as x is distributed as a normal distribution with mean mu and variance sigma squared. Now, depending on who you are, the computers like this to be sigma. Some people will write it as sigma, some people will write it as sigma squared, and that's going to be totally up to you on this, which one you're going to use. The CDF has no closed form solution, so either tables must be used, or better yet, a computer. All right, so some things that you can work out from this if you want to play around with the math. The expected value of this thing is mu, which is the mean. Hey, that's nice. Easy calculation. If you know the mean, if you know mu, then you know the mean. The variance works out to be sigma squared. So everything is what it is named to be, which is really nice. So the parameters are exactly the mean and the variance, and this makes our life very nice. So what does the mean do, or what does mu do? So it controls the center of the distribution, which happens to be the highest point. Here's mu. I've drawn a line here just so you can see that it is the mean. And remember, the mean is the balance point, and this thing's symmetric, so you should expect it to be there. Sigma squared controls the width of the distribution. So I've got two distributions that are normal distributions here, and you can see sigma 1, the width is not nearly as wide and is far taller. Where here we have sigma squared, or sigma equals 2, and you can see it's much lower and more spread out. The bulk of the probability is going to be spread out across this. All right, so let's look at an example. So Amarova is interested in the weight of newborn Asian black bears. Here's the Greek name for it. I can't pronounce it. From experience, she knows that the newborn cubs are on average about 370 grams with a standard deviation of about 50 grams. So think about this. This thing goes from being measured in grams to being a huge bear. So just starts off really, really small. So a mother gives birth to a cub weighing about 450 grams, and Amarova is interested in whether or not the this is an exceptionally rare phenomenon. Is this uncommon or is this common? Hence, she is interested, what is the probability she would see a cub larger than 450 grams? So here's basically what we know. We know mu is equal to 370, sigma is equal to 50, because it was represented as a standard deviation. So we want to know the probability that x is greater than 450. All right, so this is the area we wish to know. Now, the problem here is that the CDF gives the area to the left, so we're going to have to use the 1 minus trick on this thing. So we're going to use the complement. This is the CDF, so we can easily plug it in there. And if you're using a computer, which I highly recommend you do, in R you could calculate this by using P norm. 450 is the value we're interested in. The mean is 370 and the standard deviation is 50. If you're using Excel, put equal signs, norm.dist, 450, 370, 50, and true, so, because it will give you the cumulative distribution function. And they both give you the value of 9452, 0.9452, which it still needs to have work done on it. This is not the answer, right? Because we're using the complement. So 1 minus this, 1 minus 0.9452, we get 0.0548. So this is probability of about 0.0458 of seeing a bear cub this big or bigger. I wouldn't consider that exceptionally rare. And that was what her question is. Is this an exceptionally rare event? And really, it happens about 5% of the time, or 1 time in 20, if you want to look at it that way. So it's not incredibly rare. All right, so here's a quick summary. The PDF, this is what it is. The CDF, not tractable. We're going to use a computer. And the mean and the variance are really easy because they're the parameters of the distribution. All right, on the next video, we're going to look at the standard normal distribution, which is a version of the normal distribution that most people work with because the mean is 1, or the mean is 0 and the variance is 1, and we can think about it easier than having to think about every possible normal distribution. So see you there.